Okay. Today we're going to finish up believe it or not, the last set of technical slides in this course. We'll have a little bit more next week on some various applications, but it'll largely be just the same stuff. Also looking at some recent work in the area, talking about how that relates to what we've done. I think a lot of the work in smart grid and in energy systems in general, at least on the computational side, can really put in this kind of framework very nicely. So we can do a lot with this kind of framework. I'll also remind you at the end of class to mention about the homework. I'll wait till everyone's here, but both the last homework and the homework giving it back, I didn't quite get them ready, but I hope to have it actually tonight. So if you want to pick it up tomorrow, the graded problem set 3s, you can do that. And I'll repeat that again at the end of class. The other thing is, actually, I'll just wait till the end of the class to give other announcements about the homework, since everyone should ideally be here for that. So where we left off last time was that we talked about this control of stochastic systems. So before, in the last set of slides, we talked about control, both in terms of PID control, in terms of LQR control, and then control to optimization. But we really focused on deterministic systems, right, where we knew how the system would evolve given certain inputs. So that made it kind of nice because we could plan over a very long time, just take those controls, and what we would get in the end is something that would just work over that long period of time. But in stochastic systems, as you might imagine, things are a little bit trickier. So today, what we're going to talk about today is a few cases, and in general, I should say, this is sort of what I ended on last time, was that in general, stochastic systems can be much, much harder to control, right? Because you can imagine that instead of just having a single state that you worry about, you have a whole distribution over possible states the system can be in. And you can have all sorts of interesting functions of these distributions and how you handle this different distribution. That can be very hard to even propagate through time, let alone figure out how to control through time. So in general, these problems are very hard. But the good news is that there are certain cases where we actually can solve these problems analytically. And we'll cover 2 of those today. Again, kind of briefly, because the details here can get quite involved, and I don't want to get too much into them. I want to sort of give a broad overview. But the one we will focus on for a while is a case where you cannot solve it exactly. So linear quadratic systems and Markov decision processes are both cases where for some limited situations, you can solve the optimal stochastic control problem exactly. Model predictive control, or MPC, is a slightly different paradigm in that it's not actually an optimal strategy. This is not the optimal way of solving systems, but it is a heuristic that works extremely well in practice. And it kind of brings together this the optimization-based framework for control with methods that can actually work online, and which can work, by that I mean sort of you can execute them as you go, and which can work in these stochastic environments. So that's going to be outlined for today, and hopefully we can get through all that. If not, we'll finish up briefly next lecture, and then we'll talk about some applications as well next week. So to start off with, are there any sort of broad questions about what we covered last time, or this overall outline here? Okay, great. All right, so let's start with this, our favorite nice, easy system we can actually solve here, which are linear quadratic systems. So remember, we have the same idea as before. We had a linear system. So xt plus 1 equals axt plus but. Again, here a and b are known. And our objective we want to optimize is the sum of some quadratic terms. So the cost is quadratic. System is linear. That's the linear quadratic part of this setting. But unlike before, where we just had this bit here, right, where it's just deterministically equal to ax plus bu, in our new setting now we have some noise. In particular, we have Gaussian noise, which I talked about a little bit before. Basically, Gaussian noise is a generalization of single-variate Gaussian random variables to the multivariate case, right, where you actually take a whole bunch of single random Gaussian variables, multiply them by some matrix, and that gives you a new variable epsilon t. Okay, and what we're having here is and epsilon t is 0 mean, so an expectation is equal to 0. but it is a random variable. So we don't know what the next state is going to be given the current state control input. We just know what's going to be in the expectation. So this is a little harder problem now, it seems like, right? Because now, it's unclear what we should really do. How do you account for the fact that you don't know where your system is going to end up? And I didn't go through the derivation of LQR, so this will even be more, even for the deterministic case. So this will actually be even more probably hand-wavy and high level here. But the only point I want to make is this kind of remarkable fact, which is the LQR solution to this system, where you ignore the noise, is actually optimal for this system where there is noise. And what's kind of incredible about that is that this LQR solution that we computed before, I mean, it's one line of MATLAB code here, did not depend at all on any noise term, right? We didn't know anything about the noise. You might think that, look, if the noise is really high, you might want a different strategy than if the noise is low, right? If this is sort of a very small number, which would correspond to being sort of not having very much variance in your noise or in your state, you might expect that you want a different control strategy than you would want if things were very, very noisy. And amazingly, that ends up not being the case. So again, if anyone's curious, I can point them to some references on this. But the take-home message is just that the same solution works in this setting as did before, with no dependence on this term epsilon, this term sigma here, which is the covariance of the noise. And that's really surprising, actually, because you would not expect that. And it falls out, and actually I'll give a little brief intuition about why this is, but this is a pretty remarkable fact. Again, we didn't even go through the derivation for LQR, as I said, so it's going to be very high level, this explanation here, and not rigorous at all. But hopefully I'll give you some intuition about why this might be true. So the basic idea is that, remember, what we mentioned before was that a nice thing about linear Gaussian systems is that in expectation, you could still talk about the expected value of the state progressing according to this linear system here. Right, so what we said was for normal, or for arbitrary, nonlinear, potentially, stochastic systems, that is, if xt is of this, xt plus 1 is of this form, xt plus 1 equals just some potentially nonlinear function of xt and ut plus epsilon t. Even if this epsilon t term is Gaussian, we do not have the fact that, right, so that means these are all random variables, so we have to talk about their expectation perhaps, but that does not imply that the expected value of xt plus 1, this does not necessarily equal f of the expected value of xt ut. And essentially the basic problem here is that expectations do not carry through when you have a nonlinear function here. And remember what we wrote out last time, and you can go back and look at the notes for just stochastic dynamical systems, what we saw was that because due to this property of expectation, which is a linear operator, so we can distribute expectation along sums, it turns out that essentially xt plus 1 for any xt, so this is for xt plus 1 far in the future. So say we only know x1, and we want to talk about xt far in the future from that. The expected value of xt plus 1 will still be equal to a times the expected value of xt plus bu. And what it really happens here is that you get, when you write this all out, you get a lot more, you'll get a, something like a epsilon t minus 1 plus blah, 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 blah. So you'll get a lot of extra noise terms here. But because actually I should say expectation of this thing, you'll get a lot of extra terms in this sum when you sort of just expand it out iteratively. What happens here is that these are all zero mean. And so you can take the mean individually of all of them, and they all cancel out. And we did this last time in the lecture a few before Thanksgiving, so I won't do it all again. But the basic idea is these terms all cancel out. These are all equal to 0. And so we have this very nice property here. And what this means is that we can think about our state far in the future without necessarily worrying about the precise distributions, at least the expected value of the state far in the future, without worrying about the precise distribution of states in the meantime. And that's sort of the key property here. The other key property is that there's this very nice property of quadratic costs. And that is, if we take the expectation of some matrix Q times xt, this is now not linear. So it's not just equal to this. But and I should actually highlight here, this is only for Gaussian random variables, and very, very importantly. But for Gaussian random variables, if x is a Gaussian random variable, and in fact it is Gaussian, x itself is Gaussian with some covariance here, we actually do have a property like this. Right? So the expected value of some quadratic norm term equals the quadratic norm term of the expected value plus some additional constant term, where this constant term, of course, does depend on the covariance of the variable. Okay, but this is actually a pretty surprising fact as well, because almost very rarely can you sort of write what expectations of nonlinear functions are, because when you have nonlinear functions, expectations no longer just apply linear rules here. But for Gaussian variables, and I should probably put that in the note or in the slides explicitly, but because it's very, very important. This only holds for Gaussian variables, but for Gaussian variables, this is in fact the case. And now the high-level idea is, because of these two facts, when you write out the solution for LQR, what you'll find is that even though this constant term depends on the covariance, you actually cannot, doesn't matter what actions you take, you will have no effect on that constant term, it turns out. So it doesn't matter what actions you take, does not affect. So basically the covariance of the system will not affect, and how noisy it is will not affect what actions you should take, because you cannot control that element of the noise. And so it winds out that there's actually no effect on the noise in terms of the solution. The only difference is your actual cost to go function, this function j, will be higher than it was before, because now you actually have to have this extra term that accounts for the stochasticity of the system. So essentially, using this thing here, right, what you get is you get that j of this whole thing here equals j of the expected values, where you replace this an expectation here, plus some extra additional term here, which you can't do anything about. So that's kind of surprising, but it's a really kind of remarkable fact about LQR that does not matter. It still is optimal, even in the stochastic setting. And remember, LQR gives us this control law, ut equals k xt, maybe where k is time varying if you do it in the finite horizon case, or it's fixed if you do it in the infinite horizon case. But this is sort of also kind of, it's natural to see how this actually can account for noise, right? Because this tells you our control is always some function of the current state. So if the state has a little bit extra noise in it, we'll just account for that in taking new control actions. Right? It's not like the optimization approach where you get some fixed set of controls. You always base your current control on the current state. And so you actually can account for the fact that you are maybe deviating a little bit from where you thought you would be. So again, this is all very, very high level here. I just want to show what happens when you actually do this now. So let's take this generator example. We'll add noise to the angular velocities of the generators. What this corresponds to is, for example, a little bit of noise in the loads that are turning on and off. So remember, and I'm going to possibly make an error when I write this equation without seeing it anywhere. But remember, our update equation for omega, so omega dot in the differential case, this is equal to 1 over 2h, that was the moment of inertia, times, what was it? It was like b, g, g, minus b, g, l, b, l, l inverse, b, l, g, times theta, right? That was our term that depended on the angles of all the other generators, how they were all coupled together, and these b terms were just the partition form of that DC power flow matrix. This plus B G L B L L inverse P load. These are the loads of external things. So adding some noise to this, right, adding some random noise, that's actually equivalent to saying there's some extra noise in the load. We don't quite know what the loads are. You know, maybe we know what they are in expectation. We know their average value, but they're going to fluctuate a little bit, right? And this is, of course, guaranteed to happen in reality, right? The loads, external loads that generators cannot see, those are going to vary some. So this is adding noise here corresponds essentially, if we sort of say maybe this is actually P plus epsilon t here. I'm actually putting this in this equation here, but remember this would just be multiplying some matrix times some Gaussian random variable, and that's the same as some other Gaussian random variable. So this is just adding some, so this is the same as some sort of plus epsilon tilde there with some other distribution. Okay, so don't worry about that if you didn't understand it. If you know sort of more about the probabilistic notions here, that's great, but if you didn't quite follow that, don't worry. The only thing I'm saying is what I'm doing here is I'm adding a little bit of noise in the loads that people are actually turning on and off. Which is, as I said, something that will always happen if you're actually running a generator. You don't know that everyone's going to keep their lights on the exact same amount. In fact, you know they're not going to do that, is what you know. And what happens is, remember LQR, and I guess I should probably put this up before, but LQR, if we just plotted what happened in the deterministic case, these things kind of they started off with some little bit of trajectories here that got the system from its initial state to its desired state, but then they kind of leveled out at the nominal input, right? The ones that kept the system at that state. What happens in the stochastic case, though, is that there's some variance here, right? Because the system always has a little bit of disturbance. It's as if it really is, that you're never quite where you want to be, right? X is never quite equal to the desired X. And so you're always going to apply a little bit of control to account for this, right? And so what happens when you look at the control is that these control that you execute actually kind of bounces around some, to account for the fact that there are actually disturbances in your states that you're trying to smooth out. So, do you have any questions about that? Because you're going to see a lot of plots like this in the rest of these slides. So it's worth understanding what's happening here. Yeah? Yeah, I mean, right. So I'm adding random noise here to the velocities, and that's probably not a great model of what really happens in practice, right? Because it's probably not like, at 1 second there's just some random addition to that, and then the next, or not even second, but fraction of a second, there's some completely new random fraction. You probably would have a slightly different notion of randomness here than what I'm doing here, but it's actually not a horrible notion, and but yes, that's what causes that roughness to it. You can add constraints that sort of would try to penalize roughness. So we talked about a little bit, at least in the setting of optimization-based control, you could add, for example, constraints on how much you could change control from one time to another. You can do that a little bit with LQR. Again, you have to have just quadratic penalties on it, and you have to actually augment the state a little bit in order to do this. But you can do similar things, but it's not trivial there. So what's common here is because we sort of have sort of this second order system, right, where theta, we're adding disturbances to the velocities of theta, but not to theta itself. So theta itself doesn't look that bumpy, because it's just its velocities kind of going up and down a little bit. Whereas to account for this, because we can sort of sense the immediate change in velocities, the controller will actually output some stuff that kind of varies more like the noise actually varies. It's not random here. There is obviously some sort of smoothing involved there, but there is also kind of a noise factor as well. Now you might say that, well, this is nice, but I don't really like the fact that it doesn't quite ever get there. And the reality is, in stochastic systems, you have to kind of deal with the fact that the system is never going to quite get to its desired location, right? You can't fix it at 0, because then random noise will push it away from that, and you have to take some action to correct for that, etc. You can push it closer to 0 by using higher control inputs. And that corresponds to higher gains in our LQR controller. So remember, LQR has this cost where we penalize both the deviation from the 0 state and deviation from the 0 control, which could either be actually 0 or they could be the desired control in the desired state. And if you decrease the penalty on the controls, well, LQR will then actually result in, what will end up happening is you get bigger entries in that K matrix, and you'll be more aggressive about applying control to account for errors. And so what happens is it looks like this. Is that now all of a sudden, it looks in this graph, it's like you're doing it better. You also converge faster because you're using really big control inputs there. That was the problem, remember, also from last time. We sort of said you didn't want to do that because this actually goes way, way down to very, very large inputs. But when you actually converge then, what happens is that you do get sort of tighter regulation around the desired point, but you do so by using a lot more control inputs. And now, which one of these is better? That's kind of an arbitrary distinction, right? Because which one is better here depends entirely on the cost that you care about. And that's exactly what you told LQR. So for the cost that you give LQR, these are both optimal strategies. This one just says, I care a little bit more about having smaller control inputs too, whereas this one says what I really care about is just tighter regulation around the desired point. Does that make sense? Any questions about this? The same, I should also add, goes for PD and PID control. You can get very similar behavior with PID control and with PD control for stochastic systems too. PID control actually can be kind of nasty in stochastic systems because its integrators can build up over time and sort of swing back and forth a lot. But you can still take care of things like that as well. So the overall point is that these kind of considerations apply both to PID control and to LQR control. The idea is that these methods do, in some sense, naturally account for a little bit of stochasticity because they are feedback methods, right? They're always telling you what to do based on the current state. So they always, and if the state deviates a little bit due to some noise, it'll push you back to the state. And so they both work well for that reason. One final note is that, also amazingly, it turns out that in the partially observable case, so now let's get even more complicated here, right? So before we had just this bit here where there's stochasticity in the system, but we always would find out the true state. We'd always would observe that. And so we could take our actions based, remember, LQR gives you this, right? LQR gives you U equals KXT. So you have to know what the current state is in order to take the LQR action. What's even more impressive is that, let's say we're in this partially observable setting. In fact, a noisy partially observable setting, where our system is stochastic. It's linear, but it's stochastic with some Gaussian noise. And we don't even observe the true state, right? What we observe is actually some noisy function of the true state. And if you remember back to the lectures on dynamical systems, for the linear case, we had a very nice way of estimating, getting our best estimate of the current state, given all this. And that was a method known as the Kalman filter. And the Kalman filter was kind of like a least squares estimate, our best estimate of xt, given all our past data, but realizing that we can never know it exactly because there's noise here. We can never be quite sure that we have the correct xt. So what's really incredible here is that this simplest possible strategy you would sort of think of actually ends up being the correct one. So I mean, what should we do then? You know, we don't know the true state, so let's estimate the state with a Kalman filter and say get some estimate x hat, and then just take our control actions based on our estimate of the state. And what's really incredible here, again, in the LQ setting, and I know I keep saying that a lot, but it really is amazing these things are true because they don't hold almost anywhere else. You will never find these things to hold. But what's interesting here is that this actually ends up being the right thing to do, the completely optimal thing to do. You use a method called the Kalman filter to estimate the current state based on all your past observations. It does not give you the actual state. It just gives you some estimate of what you think it might be. It's not going to be the right one. Then you take your control actions using LQR, which knows nothing about stochasticity of any kind. You take that control action just using your estimate of the state. And that actually ends up being the best thing you can do. I have every possible strategy. That is the optimal one. This is known as the separation principle, because there's a separation between the estimation portion of the system and the control portion. And this is the only, I think this is about the only setting where it actually holds, in fact, this separation principle. It's also, there was this algorithm where you use a Kalman filter and LQR is also something called LQG. So you see that acronym. It's just LQR with a Kalman filter. But again, it's the best thing to do here, but it's extremely rare that it actually is the best thing to do. Not very common at all. Okay, now don't worry if some of this was a little bit fast. It was meant to be fast, and we're not going to, none of the homework problems are about LQR or anything like this. The point of all this is sort of give you a broad overview of the types of methods that are used in practice. So what's important to take away from this is that for linear quadratic systems, in the deterministic case, there's a very nice solution called LQR, and you can compute it with one line in MATLAB code, this dLQR function. That's nice. Second thing is that in the stochastic case, where you can observe the state, you actually just do the exact same thing as before. You don't change it at all, and that is actually the best thing you could possibly do. And then finally, even if you can't observe the state, well, we have this other algorithm called the Kalman filter, which we know to be good at estimating the state given that. And so all you do in that case is you apply Kalman filter to estimate the state, and then you apply LQR to control the system. So if you want to know more about those precise methods, there's lots of courses here you can take on those things. So this certainly probably would not be enough to get you very far with these methods, but it's very good to understand that these things exist, and this is the kind of ideas people use to control systems like this. Actually, as a show of hands, has anyone here seen these methods before, LQR? Has anyone seen LQR before? By show of hands. And a Kalman filter, who's seen a Kalman filter? Or heard of a Kalman filter? Okay, So okay, so you know, as I said, these are not going to be. You cannot implement any of these things right now. You could probably look up on the web and learn enough to implement them, but you certainly could not implement them yet. But it's just good to know sort of the overall outline of these things. And we're actually going to use a method for the homework that's in some sense more advanced than a lot of these things. So you're actually using something that's even newer and later and greater. Okay, so I'm going to spend most of this lecture talking about this next thing, which is model predictive control. But I want to take a brief moment to talk about Markov decision processes. Because it is a setting that, again, you will see a lot, and you might see people talk about MDPs a fair amount. And so it's good just to know the terminology here and know sort of why it's important and how you go about solving these things. So again, we talked, and I'm actually not even going to give an example of these. I think some people actually are doing similar things for their problem assignments, but we won't worry about that just yet. Or for their final projects rather, but we won't worry about that here. But the MDP case is a situation where you have, it's really actually a fully general description of stochastic systems I mentioned before. The only difference is that you typically think of it in states that have, or in systems that have a discrete number of states. So before we talked about a state being a vector in Rn, right? And now I'm talking about a state just having n elements total. And in fact, this is a very limited descriptor, right? Because to describe a vector, and even a vector in R, a single-dimensional vector that can take any value, you would need an infinite number of states, right? So you sort of take this continuous state where your state can lie anywhere along this line here. You need to sort of chop it up into many different pieces and say, okay, I'm going to say anywhere in between there, I'm in state I. And to discretize states like this, which is a common way of transforming continuous systems to an MDP, as you can imagine, requires a whole lot of states. So the n here should not be confused with the n of the dimensionality of a state, because this n for equivalent systems would be much, much bigger. Okay? But let's just say, you know, there are actually some domains where you genuinely do have discrete numbers of states. A system can either be on or off, or you know, some machine can be in one of k different possible states. So it's worth thinking about this at least. And because you can actually solve these cases for general stochastic distributions, oftentimes people use this formalism even when you can't express the state that well, or even when it's a bad approximation in terms of actually expressing a system. Okay, so I had this all before. This was all on the last slide too, so I'll just go over it quickly. But the state is a number from 1 to n, a discrete number. The control is also a discrete number from 1 to m. The dynamics of the system are governed by transition probabilities. So the matrix P, or actually a lot of matrices P, one for each different action, where the probability of ending up in state J, given to your state I and take action K, is just some entry in this big matrix here. And don't worry about the precise notation here. All I'm saying is that you actually have to have a specific enumeration for every single current state, next state, and action about what the probability is of that sequence for every single possible state, action, and next state. And then finally, you also have a cost function, which takes as input a state and a control, and it gives you some cost. You also will see this sometimes as written as a reward function, which is just negative cost. So we've been talking about minimizing cost of a policy, right? Minimizing cost of our actions. You could also talk about maximizing reward. Say you know, every time you don't turn on the generator, you make some money. So you can talk about maximizing your profit from this. They're really equivalent here. Cost is just negative reward. So they're the same thing. Now, very, very briefly, interesting thing here is that you actually can come up with the optimal policy for how to behave in an MDP. You do it using a method called value iteration. There's other ones called policy iteration too, which are a little bit different. Those are actually more natural in the infinite time horizon case rather than the finite time horizon case. You can also have value iteration in the infinite time horizon case, but it's really kind of the simplest algorithm for the case where we have some finite horizon that we're maximizing our reward over. So the idea is we're going to iteratively build this optimal cost to go function, J star. It's also called a value function. And what this value function says, and I guess I didn't really write it out explicitly, some definitions of it, but basically J t of x, very informally, equals the cost to being in state x at time t. So this is really x is, remember, a number here, just a number from 1 to n. And so this function, I'm writing it as a function here, but really it's just going to be a big vector. Right? It's going to be a vector for all the states, what the value of that state is. So it's the cost of being in the state at that time, and I should say the expected cost. Expected cost. And acting optimally thereafter. That's kind of a little bit ambiguous what I mean by acting optimally thereafter, but just doing the best thing you can afterwards. And the way you build this is a method called value iteration. It also goes by the name dynamic programming. It's a general technique, I guess, that this is an instance of. But the basic idea is, look, if we are already at time t, big T, then there's no cost to acting optimally thereafter because we're done. We're over, right? So you could conceivably then build an optimal value function for time t. It just says at time t, just take whatever action has the lowest cost, because you're not going to change what your next state is. So just don't take a really stupid action. Then what you do is say, okay, well that's true. That gives us the optimal value function for time big T. And what we do then, and again, by optimal value function, I mean we have a vector that for every state it tells you what the value is. And then what we do is that we repeat going from t minus 1 down to 1, and we build this value function iteratively. So the idea is we know, we've figured out essentially for j big T, that tells us what to do and how to act optimally when we're at time big T. Now if we're at time big T minus 1, well, the best thing to do is to act optimally for that time, and then do whatever is going to be an expectation best for the next time step. So what this is saying here is we minimize for some other t, little t, which we iterate from t minus 1 down to t, we set this optimal value function to be the minimum over all possible actions of the cost of that action, because we do have to incur some cost for that action, plus the sum over all possible next states given that action, and the probability of winding up in some new state given we are in state x and we take action u. So this term here, remember, is just the probability that we're in state x prime given that we're in state x and we take action u. And then we are penalized, we're penalized by this cost to go for that next state. So this term here is really just the expected value of acting optimally for thereafter. And again, this is an aside. Hopefully it will relate a little bit about what we've been doing so far to MDP. So if you see them in the future, you'll have some idea about what this is. But again, I'm not trying to describe this to a point where you can actually implement it. So you do this. You compute this value function here for all possible states and all possible times ranging from time t plus 1 to t minus 1. And this is called dynamic programming, sort of an interesting, kind of very catchy name, but basically all that it means is that we're using our future computations we're using our past computations in computing our subsequent computations, right? So we're using this J star which computed at the previous time to do our next computation. And that's all that dynamic programming really means in this context. Finally, once we've done all this, now we have the optimal value function. So we know what the cost of being the state kind of is, right? But, and this actually is sort of a weird notation here, but don't like this. So then given that we know the optimal value function, to actually take an action, so say we're in state X and we want to know what action to take, all you do is and this is actually bad notation here, but all you do is you look at this minimization here, and you pick the U that actually minimized this. Right, so all you do is just pick the U that minimizes. This is actually not just bad notation, it's actually incorrect because the J already has minimization built in, so ignore this. The policy you take is just look at the U that actually gave you that minimum cost and take that one. And one that's kind of interesting here is that in this setting, it's actually hard, and I won't talk about this too much, but it's actually hard to use an optimization-based approach. I should qualify that, to use a non-value function-based optimization approach. So in linear dynamical systems, for example, we could just optimize over U, right? Over the sequence of all U's and over X's. Here, actually, if you try to do that, it ends up being not linear because this, the fact is you actually have U and X in the same kind of thing here. So for technical reasons, it actually does not end up being an easy constraint to satisfy. So it's actually kind of hard to set up an optimization-based framework as we did before. You can write this as an optimization problem just in terms of the value function, not in terms of the actual sequence of controls you take. That's kind of a side note there. It's just that this is actually something where it's a little bit different than what we've seen before. So this is all I'm really going to say about MDPs. If people are interested, I know people are, as I said, doing some for their projects. So you will, in doing that, have learned a lot more about them, I'm sure. But this is just sort of an aside because it is a system that comes up a lot, and it's also an instance of a stochastic system where we actually can solve it optimally in some cases. As long as the number of states, number of controls aren't too big, we can actually solve it optimally. The final thing, though, is that, so again, this method is really only doable when the number of system states is small, and so we can really enumerate all possible states and all possible controls. There are approximations you can use in other settings, I should add, too, but I'm talking about the exact case here. This is really what you have to do. As I said before, the problem here is that for continuous state systems, you'll typically need a whole lot of discrete states to really capture the dynamics of a continuous system, and making it sometimes just completely intractable to really do it. Another important point is that unlike the LQG setting, the linear quadratic Gaussian setting, which was the stochastic system we talked about before, here, if we don't actually observe the state, the partially observable setting for an MDP, this is no longer easy to solve. This makes things much harder, and it's, again, if you know terms from computation, this actually ends up being an MP-hard problem to solve when you don't know the true state. This is a domain called a partially observable MDP, or a POMDP. There's lots of work on these areas, and people have some good heuristics that can sometimes work okay for relatively small systems, but they are very, very hard to solve exactly in the general case. So again, it kind of actually makes the LQG setting even nicer than we thought before, maybe, because we can solve the partially observable case there. The separation principle that we had there does not even come close to holding here. So even though we can solve it exactly in the fully observed case, it does not mean we can solve it in the partially observed case, observable case. And those are just sort of high-level points to take home. LQG, do it optimally, stochastic, and partially observable. MDPs, you can do optimally in their natural stochastic setting, cannot solve them easily in the partially observable setting. Okay, so that actually was all sort of prelude to what I want to talk about for the rest of this lecture, and I might end up going over to the next one as well. But the idea here, and it's one I've kind of been hinting at this whole time, so this is actually what you are doing for the homework. I guess the 15.830 is doing this for the homework. It's sort of, you're only doing part of it in 15.630 homework, but it's still very important to know. So this is kind of what I've been hinting at throughout this unit on control, is ways of taking this paradigm for controls optimization and applying it to stochastic systems. Systems where we don't know how it's going to evolve. And that can happen either, again, because there's some real noise, or we're just not modeling things well enough. You know, maybe we don't model, again, you know, if power changes, loads change, you probably don't want to include, you know, the mindset of every person that's changing loads as a variable in your state space. So probably when you start dealing with tractable systems, there will be some noise because there are things you're not modeling there. If you have predictions, these predictions can be wrong. So if you're going to forecast, for example, what the load will be in the future, and it's not that, that is another sort of stochastic element in your system. And we want, at the same time though, this technique of control as optimization was really powerful too, right? Because we had the ability to directly put in constraints on the controls, sort of constrain whatever we want, right? We could constrain how things change, how, you know, put absolute bounds on the numbers involved, so on the controls or states involved. So it's a really powerful paradigm, yet we want some way of handling it when things actually do change. And the problem, as I've been hinting at, but will show now, is that in the optimization approach, what we get back out of our problem is just a sequence of control actions, right? We don't, unlike LQR or MDPs, we don't actually get a policy back. Okay, we don't get something that tells us for any state what do we do. All we get back is say, take these, here's a bunch of controls to execute. And, as you would expect, if things don't evolve as we thought in the optimization time, this can cause the system to diverge, right? We can actually not get what we wanted to get. So here's the example. Here is our controller example where we use optimization to schedule the generation for all these plants in a way that would bring us to the desired state while staying within certain bounds in our control actions, right? So each one is limited to this sort of range, which you can kind of just visualize from the picture here. But basically, there's some nominal value it should be, and we can only go within a certain range outside this nominal value for the control. Now, if everything's deterministic, things are great, right? Because what happens is that, well, we predict we should take these actions here. We go ahead and execute them, and the system, as we wanted, just converges directly to that. And so this is what, because we're solving all these variables as an optimization problem, remember sort of x and u are optimization variables. This is both what really happens and what we sort of thought internally was going to happen. Actually, maybe I'll be a little more explicit there. So I won't write all the constraints involved here, but remember, the optimization as controls optimization framework was we would minimize over u1 to t and x1 to t, right? This sum from t equals 1 to big T, the cost of xt ut. That could be quadratic cost, or it could be anything else, subject to, well, first of all, we have the constraint that x1 equals whatever initial state we're currently in. And then the constraint that xt plus 1 equals a xt plus b ut. This is for all t here. So that's our optimization problem. And we could add other constraints too, but I won't talk about those here. So I'm leaving out any noise here because in expectation, maybe this is what would be happening. So if you want to minimize the expected value, it's fine. You can just treat all as expectations here. So that's great. The model will kind of figure out what to do here. And in computing this, it will give you an answer both in terms of some optimal set of control actions to take, and it'll also output some best states. And those states really are what it thinks will happen given this internal model, right? The states that we get out of this problem have to obey these dynamics, so they will in fact be kind of following the expected evolution of states. And what happens when things are deterministic is this is exactly holds. And so what we predict will happen, which is what the controller internally thinks is going to happen, is in fact exactly what does happen. Now the problem is when there's noise. So when there's noise, we still actually solve the same problem here, right? Because now it's just talking about expected values. For a lot of, I guess in some cases you wouldn't quite have expectations work quite as well here, but in general you have expectations here, and you could just basically write everything in terms of expectations of x instead of the actual variables x, right? And this framework here would still hold. The problem though is that when you actually run the system, what happens is this. So we have the same controls. Internally, we ran our our optimization procedure, and we think, okay, here's what's going to happen. This is what's going to happen here. We really run it in the system, and because there's some noise that we didn't know about, what happens is this. And that will never go away. And if we had a very long time, it actually even get worse, because we would just keep at these values here, and things would just kind of keep going off. So we're not really regulating the system at all around this desired point. And this seems like a big problem, right? Because unlike LQR, we don't have any kind of way of feeding back what's really happening with our states to know what to do. So what do we do? The intuition, I think, is that, as you would expect, sort of what happens at the very beginning here looks a lot like what we expect to happen, right? Because at the very beginning, there isn't much noise. There doesn't have much chance for noise to build up, so things are fine. So maybe for this amount, or in the in the extreme case, just for exactly one time step in our discrete system update, this is probably a pretty good control strategy. So all we do is we say, okay, this was good for the first time, and it got kind of bad out here. We take our optimization problem, we optimize over the whole part here, but then we only take the first action we get back. Right? And then we see what happens. We repeat the process. Rerun the optimization problem, see what the first action is, and take that action. So here is the actual model predictive control algorithm. And as you can imagine, it's kind of complicated, right? Sort of hard to really, because you're optimizing it every time you're solving a new optimization problem. And then you're just taking the kind of the first action. You're not taking all the actions you actually take. So the idea is we have this procedure, this optimization procedure, that will give us good actions. The problem is, in the far future, this can get kind of bad. So all we do is we rerun this procedure at every time point. Then we take only the first prescription of that set of actions, and we repeat the process. So a little informally, I guess, what happens is we're going to repeat for t being equal from 1 to t, 1 to big T. So that's our actual control task horizon we're really worried about. We observe the state of the system, right? We can see what it is. And then we solve this controls optimization problem, I'm writing one instantiation where you have, say, bounds and the controls and the states. We solve that using some different variables, which I'm calling x tilde and u tilde. And we solve it over some different horizon, which I'm calling h here. And really, h could be, I mean, in the sort of closest mapping to what we're doing before, I guess h would be t minus little t, because that would be planning for the rest of the true time horizon. We're going to plan the rest of our actions, right? So what we do is we solve this problem here with these x tilde and u tilde variables. And it's important to understand that we are solving this problem for a long time in the future, under our expectation of what's going to happen, with the first state of this initialization equal to the current state. So xt is always kind of the x init of our optimization problem here. Then we get some set of optimal controls out of that, and we pick the control that was just the first one we prescribed there. We repeat the whole process. Okay? So essentially, this is a way of treating the entire optimization procedure as a control policy, right? I mean, LQR gives a control policy. It said, multiply the state by some number. This is a control policy too. It says, solve this optimization problem and tell me the first answer you get out. You know, the first control you get back. That is also a way of going from xt to ut. It's a little more complicated than before. Okay. In this paradigm, it is confusing the first time you see it, because you sort of think about, you sort of think of control as one thing you're scheduling here. You know, these x tilde variables, they aren't even real, right? They're just sort of things we're hallucinating to sort of decide what the first thing to do is, which is kind of strange too, because we're throwing all the rest out but that first one. But this is a very, very powerful paradigm here. It finds a ton of use in actual control systems, and especially in a lot of work on electrical systems. More things like scheduling rather than maybe control of a generator or something like this, for reasons I'll talk about actually shortly. But this sort of paradigm, beyond just energy systems, which it already finds a ton of application in, it is an incredibly powerful technique that you will see all over the place if you look at sort of real industrial control processes. So, are there any questions about this? I know it is, yes, it's confusing the first time you see it. But are there any questions? Do people sort of get the broad idea here? I guess the 15-830 students will have to get it because they have to implement it on the homework. But the rest of you can get it conceptually, and that'll be good enough, I guess. Are there any questions? Okay. So let's see what happens. Well, here's what happens. So as before, as with kind of what we saw with LQR, you start up here. So this is now a stochastic system. There is noise that corresponds to varying loads. So people are turning loads on and off that we don't know about, and we're trying to regulate the system around the nominal value given all that noise. And what happens is when you run MPC, it is in fact able to regulate it. So remember that this corresponds. This should be contrasted with this case here, where you just run the control that you got from the beginning and run it. Does not able to regulate the system. In fact, this will just keep getting worse and worse as time goes on. Here, you are able to regulate the system because you're resolving the optimization every time in this intermediate phase here. And it will stay regulated as you keep going in the future too. And the cool thing now is that we're both regulating the system and we're obeying those constraints we talked about before, right? So this is what the resulting controllers looked like, or the control actions looked like. And they still have that kind of randomness to them that we talked about before, because there's some random noise. And so you actually do want to take kind of this jagged. I mean, and you could smooth this out depending on the cost, stuff like that. But for this particular costs, you still get jagged noise like this. But you get these bounds too, right? Where things are still clipped to their actual amounts here. So you don't have to worry about LQR, taking a very big deviation. I'm sorry, I'm flipping back several slides here, but you have to worry about LQR kind of taking very big deviations that maybe some noise will push you off a little bit, and it'll take some control action that's actually unallowable, right? LQR could do that. And here you don't have to worry about that, because here, those constraints in your control actions are built in to the optimization program you run every single time step. So we're kind of have the best of both cases here, right? We have feedback that can regulate the system, but we do it in a way that obeys the same constraints we wanted and that motivated our use of optimization techniques. In fact, these can be very complicated constraints too, right? You can make very complex constraints that, like power flow constraints, which you will do in the homework, that really make the system make this paradigm very powerful. I'm going to see if I have a little more time. I also want to take a little bit of time before the end of class to talk about some of the homework issues, but maybe I'll just sort of highlight some of the positives and negatives here. So a big downside of MPC is that this seems great here. Okay, look, we have some controller that is able to stay within bounds and still regulate the system. We have sort of the best of both worlds, right? We have our optimization paradigm. We also have the ability to account for stochasticity of a system. That sounds great. The problem is this is becoming pretty computationally heavy, right? As you can probably imagine. We are solving a optimization problem every time we want to take an action. And as you guys know from running a few of these in your homework, you don't always get an answer back instantaneously, right? Sometimes it takes a little while before you actually get your answer back. And what if in that time the system has moved further and you can't do anything? So for this example, in fact, this is a 5-generator system I'm talking about here, right? This is a trivially small little system. And I'm using an integration time step of 0.01 seconds. So my dt is 0.01 seconds. And I'm optimizing over a horizon of all those 10 seconds, right, to take my actions. So actually here h is equal to t. I'm using the entire horizon at every time. Now I actually wrote this code here to do this in Cplex directly. I didn't use YAML for this. I just put it directly in the standard QP form because that can be much faster than solving it with YAML. You don't have to parse it all every time. So I wrote it directly in Cplex. I exploited sparsity really well here. I did sort of the best I could do. That still is a problem with, I guess, so integration time step of 0.1. I have 10 seconds, so it's 1,000 different XTs. Each of those is 10-dimensional, and you have 5-dimensional UTs. So that's on the order of 100,000. 150,000 variables we're talking about. Lots of linear constraints too that relate all those things together. And even with the best I can do, kind of in a reasonable amount of time, this takes about 0.25 seconds to solve, which is actually really, really fast when you think about it. 150,000 variables we're talking about optimizing over, and it takes a quarter of a second. Unfortunately, this is still bigger than this here. So I showed you this graph, but this is not a realistic graph because if I was actually running this, not on a simulator, but on a real system, by the time we had moved here, I was still trying to compute the solution for what to do 0.1 seconds ago. So 0.01 seconds, from where we started. So this is sort of a problem, right? Because the downside of MPC is that we do have this large computational cost associated with it. And compare this then to LQR, where the cost is a matrix multiplication. Right? A 10 by 5 matrix you're multiplying by a 10-dimensional vector. I guess 5 by 10 matrix you're multiplying by a 10-dimensional vector. And you can imagine which one is easier to do, right? The cost is incomparable. This takes microseconds, if that, whereas this takes a quarter of a second. I think actually microseconds would be way, way too much for this. We're talking about, you know, maybe hundreds of nanoseconds, maybe. Not even, right? Less than that. Anyway, very, very fast and very, very slow. By several orders of magnitude is the difference here. So despite the fact that this might seem like a really powerful paradigm, there is this heavy cost to it. And so a lot of a lot of what makes MPC actually applicable to a real domain depends on how fast you can speed it up, right? Can we get this fast enough to actually execute it in real time? And of course, that'll depend on the system you're controlling, right? If you're controlling a system like this that evolves in the order of 0.01 seconds, that might be tough to do. I'll show you how we can get there for this system, but this is still a pretty small system. It's a 5-generator system. So the choice, I mean, I'm advocating MPC a lot because I think a lot of tasks is very good for, but it's important to also understand that it does require pretty heavy-duty computation, and that makes it inapplicable for some tasks. Right? Certainly, especially if you want maybe to implement the logic on a little tiny microprocessor, this could be tough to do. Though there is actually work on building MPC engines for little microprocessors as well. Okay, so what I'm going to talk about next is essentially ways of speeding up MPC, but I think I actually might leave that till next time. Leave the problem out there for now. I think we don't have to do anything, even for the 15830 class or homework. We don't have to do any of the speedups. I guess one speedup is if we're going to implement it actually in Cplex rather than in YAML, but other than that, you don't have to do any fancy speedups. So it's probably okay to leave the next bit till next time. I'm going to talk about how we do go about speeding it up. And you have to do things like, maybe you don't optimize every time, you optimize every couple times. Or maybe you don't use that whole horizon, use a shorter window than that to optimize. And those are the basic ideas that are there. But I'll actually take a little break. I'll talk a little about the homework first, now that people are here at class. Actually, first, are there any questions about this, the basic things here? You probably all want to know about the homework, so I imagine it's a bad time to ask it now because you want more time for that. But if there are questions, ask me next time in class or ask now. And I'll shut off the camera for this.